Today we are going to be doing linear inequalities in two variables. So our objective is to be able to, write, graph linear inequalities and use them to model some real world type problems. Okay, so first let's just review our inequality symbols. First we have our less than symbols. We have our less than, which looks like this. If I haven't talked about the dot method, if you picture dots on each end of these, it helps you keep track of which symbol's which. So we read from left to right. So as I'm reading this symbol, I read one dot before two dots. So that tells me less than, because less one is less than two. So this is a less than. So that's a less than symbol. So we have our less than. We also have our less than or equal to. So this means you could either be less than or you could also be equal. Okay. We have our greater than symbol, greater than, which again is the other way around. Again, our dots work on this case. We have two dots first. So since I have two dots first, that's a greater than sign. Okay. Or we have our greater than or equal to. Which is our greater than or equal to. And then we're going to introduce a new one, not equal to, which is an equal sign with a slash through it. And normally it's a backslash. So, so there's our not equal to. We're going to be looking at that also today. So now that we know what our review of what our inequality symbols are, we have a linear inequality in two variables. First of all, it has to have two variables. Predominantly, we use an x and a y. Okay, we use an x and a y, and they're linear, meaning the exponents on my x and y are always just one, like x to the 1, y to the 1, and they're going to graph lines. Okay, so if you remember from linear equalities, we can write these guys in standard form. Again, our standard form for our linear equality was ax plus by equals c, right? When like your a, b, and c, we like them to be like nice whole numbers. So they could be negative. We don't normally like the a here to be negative. Basically, our inequalities is we're going to be removing this equal to and replacing it with a less than, or a greater than, or a greater than or equal to, or a not equal to. So we're going to be looking at more than just where they're equal. We're going to be looking where is one side bigger than the other, so forth and so on. Okay, so a solution of these inequalities in two variables is still an ordered pair. It's any ordered pair. Let's go back to blue. It's any ordered pair. Okay, any ordered pair that makes the inequality true. Okay, so any ordered pair that makes that inequality true. Okay, so since we're not dealing with just straight equal to, we're dealing with less than, there's usually going to be, for an inequality, for the inequality aspect, the fact that it's an inequality means there's usually more than one solution. There's usually many solutions. Okay, usually more than one solution. Usually there's many of them. Okay, and in most cases, an infinite many. So how do we denote that? How do we denote a reader which solutions will work and which solutions won't? So we're going to go ahead and look at that here in this first task. So here we have an inequality in standard form. Okay, this 2x plus 3y is less than or equal to 12. Okay, and we have the points 2x plus 3y. If we wrote this as an equals 12, okay, we could graph that line. Okay, we could graph that line a lot of different ways. We could get it into y equals mx plus b. We could also just find points that work in this situation Really, we could use what we call the intercepts. Remember when we used intercepts to graph? Basically, let x be 0. So basically, where does 3y equal 12? And that's divided by 3. That's when y is 4. So we'd have the point 0, 4. So we graph the point 0, 4 over there, which is already graphed. And then we would let the y be 0. 2x plus 3 times 0 equals 12. 2x equals 12 divided by 2. X is 6. So x is 6, y is 0. So we have the point 6, 0. And then we connect the dots. Or again, we can get it into y equals mx plus b. Here we're just graphing this line. So if I just graph this line, I end up with this blue line right here. Okay. So any point on this line would make this guy equal. Any point on that line would make them equal, but I don't want to know where they're equal. Okay. I want to know where it's less than or equal to. So here I have a bunch of other points kind of marked out here. Like we've got these points in red over here, A, B, C, D on one side of the line. And we have these points in green on the other side of the line. So let's go ahead and let's check to see which of these marked points actually work in this inequality. So again, our inequality is 2x plus 3. So I'm going to go ahead and I'm going to create a table. Choose black to start. So here's my table. We're going to go x. Okay. Actually, this is going to be an interesting table because we're actually going to put in the xy. And then we're going to say, does it work? So we're going to go like yes or no. Okay. Did that point work? Okay. So let's go ahead and let's do our first of our red points, point A. Okay. Let's come over and look at point A here. It looks like it's -1, up 1, 2, 3, 4, 5, 6, and maybe a half. So -1 up 6.5. I'm going to do it to 6.5. So again, we're going to go ahead and put it in our inequality. So 2 times -1 plus 3 times 6.5. Does that actually get me something less than or equal to 12 is my question. Okay, so let's go ahead and let's try it. Let's bring out a calculator. Oops, sorry, my calculator's missing. Okay. Okay, so we're going to take 2 times -1 plus 3 times 6.5. I get 17.5. Is that less than or equal to 12? No, it didn't work. Okay, so let's go ahead and let's try a different point. We have point B on that side as well. So let's look at point B. Point B is the point 0 up 1, 2, 3, 4, 5. 0, 5. Okay, so we have the point 0, 5. So we're taking 2 times 0 plus 3 times 5. Is that less than or equal to 12? Is the question. Well, let's see. That'd be 0 plus 15. Nope, that didn't work out either. All right, let's try point C. C is going to be the point 4 up 1, 2, 4, 2. Sorry for making me dizzy. 4, 2. 2 times 2 plus 3. Oh, I goofed. 2 times 4 plus 3 times 2. Right? Because again, our function, we'll write it up here so we can reference it. 2x plus 3y is less than or equal to 12. So 2 times 4, here we've got 8 plus 6 is 14. Is less than or equal to 12? No, that one didn't work at all. D, we have the point over 6 up 1, 2, 3, 4. Over 6 up 4, so 0.64. So 2 times 6 plus 3 times 4. 2 times 6 is 12 plus 3 times 4 is 12. That's 24. So not less than or equal to 12. No, that one didn't work either. So it looks like none of these red points up here worked. Okay. So what about the blue point? Green points. So here I have our green points, A, B, C, D, E, F, G, and H. So we have E, F, G, and H. E is the point -2, -1. Okay. So -2, so 2 times -2 plus 3 times -1. -4 plus -3 is -7. Yep, that's less than or equal to 12. So yes, that point worked. So E, now we have point F, which if we look over here is the point -1 up 2. -1 up 2. So 2 times -1 plus 3 times 2. -2 plus 6, which is 4. That's less than or equal to 12. Yes, that point works. Does anybody notice anything? E, F, G, G. Point G looks like it's over 1, 2. Oh, only 1.5. Down 1, 2.5. So 1.5 down 2.5. That will do 0.5. So 2 times 1.5. Let's do parentheses. Plus 3 times -2.5. Okay, I'm going to grab my calculator for that one. 2 times 1.5 plus 3 times -2.5. I get -4.5. Yep, that's less than or equal to 12. Yes, that one worked. So is anybody noticing? The red points up here didn't work. But so far, all 3 of these green points worked. And if I try H, H will work as well. Because this is a less than symbol. And my Y is over on this side. So all the points less than my line will work. So what we do is we denote basically any point down here will work. So we shade any point down here will work. Okay, and this is what is called a half plane. Basically, a half plane, if we come down here, a half plane is a part of a coordinate plane on one side of a line. On one side of a line. This line, which divides the coordinate plane, so here we're missing the word coordinate plane, into 2 half planes is what we call the boundary line. So in this case, my boundary line was this blue line right here. Right there is my boundary line. So that right there, and let's go ahead and mark. So that right there is my boundary line. Okay. And all the points below that boundary line will work in this inequality. So my solution set, my solution from up here isn't going to be just like a single ordered pair. It's actually all of these ordered pairs. And so again, when I said it's usually more than one solution, in this case, it's an infinite number because there's an infinite number of points down here because this plane goes forever down here, just like that line goes forever. So it's anything down here. Okay, so any of these points over here will work. So we denote it by drawing that boundary line and shading 1/2 of it. Okay, since this was not only a less than, but also a less than or equal to, that means any point that's actually on this line will work. So any of these points on the line will work because they will make it equal to. So to denote that on our graph, when it's an equal to, when it's a less than or equal to, or a greater than equal to, we do our boundary line as a solid line. If it's just strictly less than or greater than, that means that we can't include the points on that line. We do a dashed or a dotted line. And that's the same with our not equal to. We would do a dashed or dotted line because we can't actually equal that line. Okay. So to solve these linear inequalities, we're going to go through the steps. Step 1 is you graph the boundary line. Okay, so here, if I want to solve the linear inequality, it's impossible to list them all out, but I can draw a picture. We solve this by graphing and shading points that work. Okay, so we start by we graph the boundary line. So first I need to come up with that boundary line. To do that, I graph the boundary line. The y equals, in this case, 2x plus 3, which makes this one easy to graph because I know y-intercept is 3, slope is 2 over 1. So I just need to graph a line that has a y-intercept of 3 and a slope of 2. So I come over here, I draw in my axes. There's 1. Here's 2. Oh, I don't know why that's not. Okay, so there's my 2 axes. And I need a y-intercept of 3 up 1, 2, 3, and a slope of 2. Rise of 1, 2 over 1, up 2 over 1. Grab my ruler, put it on there, connect my dots. So here's my boundary line. Whoop. Okay, there's my boundary line. But I come in and notice that this is strictly less than. It is not equal to. It does not include the equal to. We don't have the equal to stuff. So it's not a solid line. I need to make it dashed. So I just come in with my ruler, with my eraser, excuse me, and I just dash it up. Let's make it a little bigger. Okay, so we dashed it. So there's my dashed line. Just take your eraser and just erase chunks of it. So this is why it's useful to either use pencil or an erasable pen, unless you just draw it dashed and don't erase. Oh, but I erased my axes. I want those. Let's fill those in. Okay, that's all right. Okay, so there's my boundary line. And now I determine, so I look at my y is on this side. And I want all the values that are, sorry, that's not a less than symbol. I'm sorry, guys. Anybody notice that? That's supposed to be greater than. That's a greater than. Okay. So now this is a greater than symbol. So I want all of the points that are going to be greater than this line. Well, greater than are bigger. Bigger y's go up. So that means I need to shade all of the lines above here. Okay. Oh, I don't like that shading. Let's get rid of that. Okay, highlight is good for this, but highlighting you can't really erase. So again, use pencil. So basically, I want to shade. I can easily erase on my iPad, so I'm going to highlight because it's easier for me to erase highlighter on here. So I want all the points up here. Okay, so we draw. So first we graph our boundary line. Okay, so step 1, boundary line. Step 2, look at the inequality. Look at inequality and shade. And then always step 3, check a point. Meaning check a point in the area where I shaded. I shaded all this area over here. So I'm just going to pick a point over here to check. It can be any point. I'm going to pick the point, I always like to pick my zeros. So let's pick this point right here. This is the point -1, 2, 3, 4, 5, -5, 0. And I'm going to check it. What I'm going to check it is I'm going to put it in my inequality. So 0 is greater than 2 times -5 plus 3. So I again put my 0 in for my y, my -5 in for my x. Is 0 greater than -10 plus 3? Is 0 greater than -7? Yes, it worked. Always check a point. Okay, which leads me to our little word of caution. Caution. Remember our rule for multiplying or dividing. Multiply, divide by a negative. You have to flip the inequality. Okay. So if you end up like doing some solving, let's say -2x is less than 6. Remember when we divided both sides by a -2? This inequality had to flip. That's what we mean by that. And you might have to do a bit of reworking to get your y by itself to be able to graph it. So don't forget that little rule. That was from a previous section. We've done those before. Okay. All right, now we're going to do, now that we looked at it one way, we started with the inequality and drew the graph. Now we're going to do it backwards. Here's a graph. We need the right thing in inequality for it. But I work it very similarly. First, I need to come up with the equation, for this boundary line. What is the equation for this line here in blue? Okay, so this is where it's important that we know how to write equations for lines. Well, I can tell right here that it's got a y-intercept of 10. And then now I'm just going to calculate slope. So here it looks like I go up 2 over 1. But be careful, this isn't 2. We're counting by 2.5. So really this is up 5 over 2.5. So instead, I'm not going to do that one. I'm going to go from here. For slope, I'm going to go from here to here because those are two nice points. So here I went up. If I'm down here at 0, I went up 5, 10, up 10 over 5 because this is 5. So here I'm up 10 over 5, 10 over 5. So my slope is 2. So there's my slope is 2. So I can write my boundary line. My boundary line is going to be y equals slope of 2, 2x plus 10. If you can't tell the slope, go back to this guy. Y minus y1 equals mx minus x1. Meaning if you can't tell the y-intercept and you can't tell the slope, use this. And again, slope is that change in y over change in x, meaning subtract your y's over subtract your x's. Okay. That's just review from previous sections. So if you need help writing those equations of the lines, these are methods you can do if you need help writing those lines. So we have our lines, but if you notice, I used an equal sign. This is supposed to be an inequality because if you notice, I'm shaded above that line. Since I'm shading above, I'm doing points that are bigger than that line. So that tells me this is going to have to be a greater than symbol. So I'm going to need a greater than symbol. And then I look at my line. Is my boundary line dashed or solid? It's a solid. This is a solid boundary line. So that tells me I'm also equal to. So there is my inequality. So we write our boundary line. And then we look at which way are we shaded. In this case, we're shaded above, so that's a greater than. And it's solid, so it's equal to. All right, last task, we're going to go ahead and do an application type problem. All right, so a realtor had a budget of $200 for cheese and crackers for an open house. So that tells me that the money I spend has to be less than or equal to 200 bucks. Because $200 is my upper limit. The amount of money I spend has to be smaller than $200. Okay, so write a linear inequality to describe the situation, graph it, and then use the graph to identify 3 possible combinations of cheese wheels and boxes of crackers. So the money I spend, I'm spending money on crackers plus cheese, has to be less than or equal to $200. My crackers are $4 per package. So if I take $4 times the number of packages, that'll get me how much money I spend on crackers. For cheese, it's $8 times the number of wheels of cheese. I'm buying full wheels of cheese. Okay, so there is another verbal model. We're just kind of breaking it down. So $4 per pack. I'm going to let X be the number of packs of crackers. Okay, this step right here is what is called defining my variable. Define the variable. I'm letting myself and any reader know what that variable is standing for. My X is my pack of crackers. Plus $8 times a wheel of cheese would be Y. So Y is the number of wheels of cheese. Okay, is less than or equal to 100. So there's my equation. I have 4x plus 8y is less than or equal to 200. Well, I kind of used up all my room. Okay, so we need to graph this. So first of all, I'm only going to be in quadrant 1 because I cannot buy negative crackers or negative wheels of cheese. So I am not going to worry about any negatives for any of these. We're just going to be in quadrant 1 right here. Okay. To graph this, I think I'm going to write it as y equals mx plus b. Maybe, yeah. Let's subtract 4x from both sides. So I end up with 8y is, I'm going to use equal to because we're doing the boundary line, is equal to negative 4x plus 200. I'm putting my 4 first, my x first, to get y equals mx plus b, and then divide both sides by 8. Y equals negative 4 divided by 8 is negative 1/2. 200 divided by 8 is 25. So this has got to have a y-intercept of 25. So I don't think I want to count by ones. I think I'm going to do every 2 is 5. So there's 5, 10, 15, 20, 25. So there's my 25. So my y-intercept of 25. And I think I'm going to do the same on this one just to keep my units the same. So because now I need to go down 1 over 2, or basically if I go down 5 over 10, wait, down 1 over 2. So it'd be like that. Down 1 over 2, down 1 over 2, down 1 over 2. I'm going to keep just taking it all the way down 1 over 2. Okay. Basically, for every 1 unit down, I have to go 2 units over. So down 1 over 2, down 1, so forth and so on. Bring in my ruler, draw in my line. I can equal this amount. So I'm going to draw it in solid because I can spend up to $200. I can even spend the $200. Okay. And then I want it to be, if you notice my symbol here, is a less than symbol. It's a less than. So that tells me my amount has to be less than that or under that line. Okay. Now, don't lose track of, again, I defined my variables. My x-axis over here is actually the number of packs of crackers. So my x over here is the number of crackers. That's why we made sure that we defined our variable over here. Oh, I don't know what that was. Okay, and my y over here is the cheese. So any point in this shaded area will work. They want me to find 3 possible combinations, so I'm just going to find 3 points in the shaded bit. Okay, so I could do, for example, and we want to buy like kind of as many. So I don't know, I could do 10 and 10. I could buy 10 of each. So 10 of each. Hey, I also could do, there's 15, here's 20, there's 25, so forth and so on. I could do 25 packs of crackers and 10. So I could do 25 crackers, 10 cheese, 25 crackers and 10 cheese. Hey, I could buy more cheese and crackers. I could do 5 and 20. I could buy 5 packages of crackers. Don't ask me what I would do with all that extra cheese, and 20 wheels of cheese. Okay, there are so many different answers here. I could use this point or this point or this point or this point. If I want to use up all of my money, it would be any of the points on the line. But maybe I don't want to use up my money. Maybe I want to be under budget by so much. Basically, I just need 3, which I have my 3. 10 of each, 25 crackers and 10 cheese, or 5 crackers and 20 cheese. There's my 3 possible solutions to stay within budget. But there are many, many options here.